Hello, historical geology students. It's kind of late here on Sunday, but I thought I need to make one more video for you for your test, which is on Monday. And let me see, it will be on February. Well, good Lord, let me see. It'll be on next Monday, whatever that is. I think it's, let me see, tomorrow's February the 8th at 7 p.m. And so I'm going to get you a test review sheet, and I'm going to send it to you through Remind and through your email next couple of days. You got a lab on plate tectonics that's due on Wednesday at 7 p.m. And then you got a lab quiz coming up next Monday as well. And you'll get it next Monday, and it'll be due by next Wednesday at 7 p.m. Lab quiz is going to cover a bunch of things. It's going to cover the metric system, sedimentary rocks, and plate tectonics. So I'm going to have a box ready for you at Monday. It'll be available at my house Monday morning for you to pick up next Monday, on February the 8th, to pick up. And then you'll do your lab quiz, and when you're done, bring back the lab box, because I need those rocks back. The box is going to contain a bottle of acid, so you can test for calcite, and a piece of glass, so you can rub the rock against the glass and see if it scratches. And I'm also going to put a little book in there for you about rocks and minerals, and you can use that in doing your quiz. Make sure you bring everything back, though, because it's the property of your own state. All right. So last time we left off talking about 1918. And in 1918, since Germany lost the war, the Allied powers confiscated the U-boats and the echo sounders. That's important because that led to the Allied powers developing their own technology for submarines and echo sounders. I mentioned before that echo sounders are used to map the bottom of the sea floor. And it was the British OSS, which is like our CIA, who carefully examined the plans for the echo sounders and noticed that the Germans had made all these maps of the bottom of the sea floor. And in the interwar years, the Allied powers continued to develop better and better echo sounders and submarines. The Treaty of Versailles would, I think, lead directly to World War II, because the conditions imposed upon Germany were very, very harsh. They were required to pay billions of dollars in gold to Great Britain and the United States, and especially France. France wanted vengeance against Germany because of all the millions of Frenchmen who died in World War I. And they took their revenge in getting some German land that belonged to Germany. Well, it was disputed land. It's called Alsace-Lorraine. They also occupied much of Germany, and they were very harsh occupiers. They used to, you can go on YouTube and see the videos. French soldiers sometimes beat German civilians up for not taking their hat off to French troops when they were marching past, and things like that. I think it created a lot of animosity from German side towards the French occupiers, and the reparations that they had to pay destroyed the German economy, so that by the late 1920s you had to have a wheelbarrow full of marks, the German currency, to buy a loaf of bread. Massive unemployment, no hope, basically. And when economic times get, when you have an economic catastrophe, that's when you have the extremists move in, um, and they fought battles in the streets in the 1920s between those on the extreme right, who were the Nazis, the Staudhelm, who were the German Veterans Association, and the monarchists who wanted to bring back the Kaiser. And on the extreme left, you had communists, socialists, and anarchists. And the rational people in the middle, like the Christian Democrats and the Social Democrats, were being squeezed, and you had these extremists fighting in the streets, pitched battles with bottles and guns and knives. This led directly to Adolf Hitler coming to power in 1933. And when Hitler came into power, that led to a massive rearmament. I'm not going to talk all about World War II. I'm just going to talk about how it leads to plate tectonics, which is the Germans developed very much more advanced submarines. And since they had developed much better submarines, they needed maps of the sea floor because they knew that they would be fighting with Britain. And let's take a look at a map of the British Isles. So Britain in those years, well, I hate this. Let's see. Britain in those years was still a major power, and you can see that here's France, and there's the English Channel, and this is the Irish Sea. And they knew that in order to win the war, the Germans had to sink British transports and prevent them from supplying the French. And the war would hinge on the success of U-boats in sinking Royal Navy ships and stopping the resupply of France from the UK. And therefore, they needed maps of the bottom of the English Channel, the North Atlantic, the Irish Sea, the North Sea here off Scotland. And so the Germans in the 30s started to through fishing trawlers and other civilian vessels started to use their echo sounders to make maps of this whole area around the British Isles in preparation for U-boat attacks in the upcoming war. And so that meant that we were getting really good maps to the bottom of the sea floor, and once if we could map the sea floor, we could figure out whether or not Wegener was right or not, whether or not the continents really are moving or not. The problem was the Germans were not sharing this with the world. This was being used by the Kriegsmarine, the German Navy, to prepare for war, so everything's top secret. And on the British side, they were developing their own maps to prepare for the war so they could sink German shipping. They needed to know how deep it was to the bottom of the sea floor so that they can use anti-submarine weapons to blow up U-boats. And by the start of the war in 1939, when Germany invaded Poland, all of the Allied side had maps of the bottom of the sea floor around Britain, around France, and we also had other allies. The United States developed seafloor maps off the East Coast, the West Coast, off of Hawaii and Alaska. And at that time, China was not communist; it was an ally of the United States. So they also shared in this technology and started to develop maps off the coast of China in preparation for war with Japan. And on the Axis side, maps were being made by all the Axis powers, not just Germany. Japan made maps all around the Japanese Empire in preparation for war using their own echo sounders. And they developed their own submarines called I-boats. The Italians also planned for war in the Mediterranean Sea, especially, and made maps using echo sounders at the bottom of the Mediterranean. So we had all the data, but it wasn't being shared because of the upcoming war. Of course, World War II occurred, and the Axis powers lost. After that happened in 1945, all of the Axis submarines were sunk. The Japanese I-boats, the German U-boats, the Italian submarines were all sunk. And the echo sounders and their data was confiscated by the Allied side. And that led directly to much better maps of the sea floor. So that by the 1950s, we had a good map of the bottom of the Atlantic Ocean. Let me show you what it looks like. In order to do that, I have to make myself smaller here. Let's take a look here at the mid-ocean ridge. So by the 1950s, we knew, let's see, the mid-Atlantic ridge, that there's a mountain range that goes through the entire Atlantic Ocean, north of Iceland, through the North Atlantic, all the way through the South Atlantic. And so that was exciting to geologists, because finally we knew, we found the biggest mountain range that existed on planet Earth, bigger than any mountain range on land. And during that time, two men, you need to remember their names, very important people, Harry Hess and Robert Dietz. Let me tell you the story of these two people, because they solved the puzzle as to whether or not the continents are actually moving or not. Harry Hess and Robert Dietz were great people. They were both commanders of destroyers in the U.S. Navy during the World War II. And destroyers are these ships that are used to fight submarines. I don't know if you've read about World War II, but the Navy developed a way of sinking submarines using things called depth charges. These are these large explosive charges that they would release off the stern of the ship, and they would explode at the depth that they were set to. They could explode at 1,000 feet underwater, 2,000 feet, 2,400 feet, wherever they thought the submarines were. So Hess and Dietz had echo sounders on their ships, and they were both patriotic. They fought for our country, and they made good maps of the bottom of the sea floor. Both of them were Princeton University professors. And in civilian life, even though they both worked for Princeton University as oceanographers, at a personal level, they didn't know each other. I think you can understand that. When you're working in a building with a lot of different people, and you don't know everybody. Some people you know real well, maybe you're friends. Others you just say hello to in the hallway to. Hess and Dietz didn't know each other personally, but during the war, they both did the same thing. They both commanded destroyers. Hess on the Atlantic side, fighting German U-boats. Dietz on the Pacific side, fighting Japanese I-boats. And they left their echo sounders on 24 hours to make nice maps of the bottom of the sea floor. And they did it for the purposes of winning the war. But as they were oceanographers, they couldn't help but be excited about what they were seeing, because they were seeing mountain ranges underneath the ocean that ran for thousands of miles, and they knew that something was going on to form those mountains, volcanism, volcanoes, and they started thinking maybe Wegener was right all along. If that at these mountain ranges you have new land being formed by the rising of magma, then the rocks will be pushed apart and the continents would be pushed apart with the oceanic crust, and therefore the continents could move. And so this was exciting to them because it suggested to them that Wegener was right all along. However, World War II was occurring, so they couldn't do too much about it. But in the 1950s, they both saw this map here showing this mountain range in the center of the Atlantic Ocean. And here you can see it runs all the way down through the Atlantic. French submariners in the 50s found volcanism occurring all along the mid-Atlantic ridge. Something spectacular happened in 1960 from something very mundane. Hess was sitting in the faculty lounge at Princeton University, and Dietz walked in, and they started a conversation about their research. And I think that meeting at that faculty lounge changed the history of geological sciences. Hess and Dietz were unknowns, and no one would be talking about them today had they not met up and discussed their data. The best way I could put it is it's just like when Lennon and McCartney met. When Lennon and McCartney met, they made the best music possible with the Beatles. Well, when Hess and Dietz came together, they made the best geological music possible. They solved the question of continental drift. And by 1962, so here's the Mid-Atlantic Ridge, a mountain range that goes through the middle of the Atlantic. But by 1962, Dietz was working on another mountain range in the Pacific. And let me show you what they discovered by 1962. They discovered that the whole planet is covered by these a mountain range that spans the globe like stitches on a baseball. Here you can see the Mid-Atlantic Ridge, and then it continues on, and it goes through. It's connected to another mountain range called the South Indian Range, which goes into another mountain range. It goes all the way through the Pacific Ocean, all the way here through the Gulf of California, and off of our Pacific Northwest and to Chile. And so these red areas show an underwater mountain range that was unknown to science, and it spans the globe like stitches on a baseball. I used to play baseball when I was in high school. I played second base, so it reminds me of stitches on a baseball. Well, we find that volcanoes are occurring throughout the mid-ocean ridge system, and Hess and Dietz came up with a new model to show that continental drift works, and it's called sea floor spreading. Here, ladies and gentlemen, you need to understand this diagram here. It's very, very important if you want to understand geology. Here's the mountain. Here's a cross section showing the mid-ocean ridge. Magma rises at the mid-ocean ridge into this gap between the mountains here at this underwater mountain range, pushing away the oceanic lithosphere. It's not just the crust in the uppermost part of the mantle. Here it says crust, but it's the lithosphere, and away from the mid-ocean ridge, like two conveyor belts away from the mid-ocean ridge. And when the oceanic lithosphere comes into contact with the continental lithosphere, the oceanic lithosphere will sink underneath the continental lithosphere. Why? Remember, the oceanic lithosphere is mafic. It's heavier, denser than the more felsic continental lithosphere. So the oceanic lithosphere will subduct underneath the continents. And the place where this subduction occurs is marked by a deep ocean trench, a very deep part of the ocean. And so there's a trench right here and here. and that marks the place where subduction occurs. As the oceanic lithosphere subducts deeper into the Earth, and we know that temperatures and pressures are higher as we go deeper in the Earth, this oceanic lithosphere will melt, and mountains will form. As the magma rises, and you have volcanoes forming mountains where the subduction occurs. So we have volcanism occurring here at the mid-ocean ridges, where oceanic lithosphere is moving away from the mid-ocean ridges like conveyor belts going in two different directions. And then when the oceanic lithosphere meets the continents at the deep ocean trenches, oceanic lithosphere subducts deeper into the mantle, and then that melts the oceanic lithosphere, and the magma rises, forming plutonic rocks and also mountain ranges with volcanoes where the subduction occurs. Think about what this means, ladies and gentlemen. That means the continents can move, because as the oceanic lithosphere moves, it pushes these continents apart from each other, right? That's how continents move. So, everybody in the world in geology knew that this new theory of seafloor spreading in 1962 by Harry Hess and Robert Dietz meant that Alfred Wegener's original theory of continental drift was true, that the continents really do move. This would lead eventually in 1967 to plate tectonic theory. Okay, plate tectonic theory. You can look it up. So, let me show you a map of the world. So by 1967, and this is the last person that you need to remember for this first test, Tuzo Wilson, 1967, came up with plate tectonic theory, which combined seafloor spreading and continental drift to make a new model to show why we have earthquakes, why we have volcanoes, why we have mountain ranges, and why they are where they are, why we have oil and natural gas fields where they are, why 95% of the Earth's geologic activity can be explained by this one model, plate tectonics, 1967, Tuzo Wilson. Let's take a look at this map of the world. You can see that the Earth's surface is divided into these lithospheric plates. And where these black lines are, ladies and gentlemen, that we call those plate boundaries. Where the plates meet, those black lines, those are plate boundaries. Okay, this is important. Please get this. Wherever the plates meet, they can do one of three things. They can push against each other. They can pull apart like they do at the mid-ocean ridges. They can push together like at the subduction zones, or they can slide next to each other. It doesn't matter how they interact. If they push, pull, or slide next to each other, stress is going to occur. Now, what is stress? Stress in physics is force divided by unit area. And we measure it in the United States in pounds per square inch. The rest of the world measures it in newtons per square meter. Stress is no more than if I push down on this table that I have here, this coffee table. I'm not going to show you my coffee table, but imagine that I push down on that coffee table, and I push down hard enough. Wouldn't I cause the coffee table to break? If I was a 350-pound, 6'5" offensive lineman for the Philadelphia Eagles, I could put a lot of stress on that table. Right? So stress can cause rocks to break. Stress is what causes earthquakes. Therefore, almost all of our earthquakes are going to occur at plate boundaries, aren't they? Think about this. Where the plates meet, that's also where you have volcanoes. Either at the mid-ocean ridges where the plates move apart, or at the subduction zones where the plates push together, you're going to have volcanoes. Volcanoes push apart the oceanic lithosphere from the mid-ocean ridges, and they also occur due to the subduction of oceanic sea floor at deep ocean trenches. Therefore, this new theory is so important. It explains why we have earthquakes, why we have volcanoes, and also explains why we have mountain building. Mountain building also occurs wherever we have plate boundaries, wherever we have these black lines. Mountain ranges occur at the mid-ocean ridges from the rising of the magma. They occur from subduction at deep ocean trenches as new volcanoes are formed due to subduction. So mountain ranges, earthquakes, volcanoes, oil, natural gas, precious metals are all found where these black lines are. These black lines can help us make money, can't they? Because if you're an oil company, you're going to look for these plate boundaries and ancient plate boundaries to look for oil and natural gas. Or if you're a mining company and you're looking for precious gemstones or gold or silver or other precious metals, they're all concentrated where these black lines are. And that's the importance of this plate tectonic theory, which came about in 1967. Now, we've got a test coming up, so after the test, I'll talk more about how seafloor spreading led to plate tectonics, and I'll talk more about why the plates move and the future of plate tectonics, and we'll get into Chapter 4. But this is all the material that you need to cover before this first test. It ends right here, and after the test, we'll go on and explore some of the more interesting stuff later on in Chapter 3.